Hello everyone. Welcome back to the YouTube channel Devotion of Knowledge. So today we are back again with our main stream of content of our channel, which is problem solving. And in this video, we are going to discuss a very interesting problem about trees, which is unique binary search trees. It's a very good problem and it is mainly a BP problem. So let us understand a question first. So question states that given an integer n, return the number of structurally unique binary search trees which has exactly n nodes of unique values from 1 to n. Okay, so in the question we are given number of nodes from 1 to n, and for that particular given number of nodes we are supposed to return total number of unique binary search trees which are possible. For example, as given in the question, if the value of n is equal to 3, then total trees, binary search trees possible with 3 nodes are, if we keep 1 as a root node, then 2, okay, then 2 and 3. If we keep 1 as a root node and second node as a 3, 2. If I keep 2 as a root node, then 1, 3 and 2 as a root node. Okay, for 2 it's only 1, and if I keep 3 as a root node, then 1 on left side and 2 on right side like this, or 3 here, 2 here and 1 here. So these are 1, 2, 3, 4 and 5 total binary search trees possible. So answer would be, output is 5 here, as you can see. So now how to approach this question? Okay, so let us find what's the main intuition behind this question. So okay, let us understand one thing. If I give you 5 nodes like this, 1, 2, 3, 4 and 5, and values of these nodes are 1, 2, 3, 4 and 5. Okay, and if I ask you a question, if I keep this one as a root node, then how many binary search trees are possible? If this one is a root node, then all of this possible will be on right hand side of this one from all these values. Okay, and on left hand side nothing will be there. Okay, next question. If I keep this 2 as a root node, then this 1 will be on left side of 2 and 3, 4, 5 will be on right side of the 2. That will be giving some another number of binary search trees to us. Similarly, next question. If I keep 3 as a root node, okay, let us solve this. I keep 3 as a root node, okay. So on left hand side, this 2 will be here, and on right hand side 4 and 5 will be here, because we are supposed to return binary search trees. So smaller value will be always on the left hand side and greater value will be always on the right hand side. Okay, so if I am keeping this 3 as a root node, so on left hand side I should have node of 1 and 2, and on right hand side nodes 4 and 5. Okay, these are just values that we are seeing. We are not returning any structure or any number. Okay, we are just telling that 1 and 2 will be on left hand side, 4 and 5 will be on right hand side. Now how many trees are possible if I take 1 and 2 as nodes? Okay, one tree which is possible is like this, and another tree which is possible is like this. Okay, so if I keep this 1 and 2, I can make these 2 binary search trees. Okay, so we will be returning these 2 trees, and similarly 4 and 5. So one tree which is possible is like this, 4, 5, and another is 5 and 4. So we will be returning these 2 trees here. So what is the total number of trees which I can make by keeping 3 as a node? Let's see. 3 was node. Left hand side I can have trees like this, 1, 2, 2 and 1, and on right hand side I can have trees like this and trees like this. Okay, so First time I can keep on left hand side this and this, and on the next try I can keep this one as my left hand side and this one as my right hand side. Okay, in another try I can keep this as my left hand side and this as in my right hand side, and in next try this and this. So basically, can you say here are two and here are also two, so total there are four combinations that I can have by keeping this as my 3 as my root node? Yes or no? Definitely yes. So how many trees we can form keeping 3 as a root node? So one can be like this, one can be like this, one can be like this. Oh, this on the left hand side. 4. Okay, I'm sorry. 4 and 5. It won't be like, it will be like this. This is one tree. 3, 1, 2, 5. Left hand side 4. These are two trees. And now taking 2 and 1. So it will be like this. 3, 2, and 1 on left hand side. Okay, I made a mistake. It will be like 2 and 1 and 1 and 2, 5, 4, 4 and 5. Okay, my mistake. This is one tree. 3, 4 on right hand side, 5. Similarly, 3, 2, 1, 5 here and 4 on left hand side. So 1, 2, 3 and 4. These are the trees that I can make. So basically, can you see that if I am having L trees on my left hand side and R trees on my right hand side, that can be formed. So total L star R are the trees that I can make. Okay, so how to approach this thing? So similarly, as I am giving you find this, let's say I take 4 nodes, 1, 2, 3 and 4. So I will be keeping this one as my root node, and I will be telling my recursive function to check that how many trees I can make using this 3 nodes. Okay, so okay, recursion function will be calling for this 3 nodes, 2, 3 and 4. So this time I will be making 2 as my root node, because any tree which will be present here, it will be having some root, some node as its own root. Okay, so it will be keeping 2 at its root node. So we'll be telling recursive function how many trees are possible for 3 and 4. Okay, 3 and 4. So here we will be keeping this as a root node, 3. So here we will be coming recursive function to be calling 4. Now there is only one node which is possible, so it will be directly returning the node. So this will return 3 like this, 3 and 4, and the next go we will keep this as a root node, and rest of the left hand side trees will be calling us by a recursive function. So basically what we are trying to say here is that 1, 2, 3 and 4. First time I will make this as a root node and this as my remaining nodes. Second time I will be keeping this as my root nodes, and all the possible trees I will be calling by recursive function, and let us say LR from this side, RR from this side. So total trees will be possible will be L star I for this particular node by keeping its root node. Next time I will be keeping this as a root node. This will be sent into recursive function again. Total possible nodes will be L star R for this node, and similarly for this node, all of them will be here and all of them will be here. So basically, can you see that here we are using some formula that if I use, okay, let us add one more node here. If I am keeping this as a root node, so I will be calling my recursive function, let us say f, for 1, 2, 3, 4 and 5. So if this is my I value, then I am calling I minus 1 on left hand for left hand side, and star f of this is n, so n minus I for my right hand side. So whatever answer I am getting this, I will be just memoizing it, or I will be just storing in dp of I, because it will be showing us that how many total number of binary search trees are possible by keeping that particular node as a root node, I minus 1 as my left hand side and n minus I as my right hand side. Okay, so this is our main approach, and base case will be obvious. If I am reaching this node, means one node, then I will be just returning the particular node. and at last we will be just taking the sum of all this and we will be getting our answer. So I hope the approach of question is clear to you, the intuition is clear to you, and right now let's jump for the code. But we will be covering both the approaches, top down approach as well as bottom up approach. So I hope approach is clear to you. Let me again just quickly recap what the intuition that we have got. Intuition is that keeping this as a root node, I will be exploring how many left entries are possible, how many right entries are possible. Right entries will be n minus I function and left end will be I minus I. And at last, I will be taking product of these two and I will get, by keeping 2 as a root node, how many total binary search trees, BSTs. Unique BSTs are possible and we will be just memoizing it in DP of I. And every time we will be doing the same thing by keeping first time for this, second time for this, third time for this, fourth for this, and eventually we will be calling initially solve of n function. It will keep first time this as a root, then second time, third time this one, fourth time this one, and eventually we will be getting answer, means summation of each and every root node, and we will be getting total binary search trees. So I think the approach of this question is clear to you. Let us directly move towards the coding part of the problem. Okay, so let us write the code for this particular problem. So initially, okay, for this we have to make the solve function int solve, and in this we will be just taking number of nodes as an input. Let us return or write the base case. It will be when n is less than equal to 1, then we'll be just returning 1, because for one node as a tree there are only total possible ways to make a tree is only one. So okay, 1. Now for int I equal to 1, I less than equal to n, I plus plus. Okay, what just happened? Instead of shift I just pressed control and it got submitted. Okay, no worries. And let us consider a left as a total number of trees that we will be getting, as I told you here. If I keep this as a root node, so let us say L as my number from getting left hand side nodes as my left side nodes, and this let's denote by R. So as left, let us say solve of I minus 1, because it will give us total number of trees which are possible by keeping I as a root node and I minus 1 as my left hand side nodes. And let us say int right equal to solve of n minus I. Okay, and let us say int temp equal to 0, and it will store total number of trees which are possible for this particular node. Temp plus equal to left star right, because as we just recently got, let I minus 1 will give us left hand side L and this will give us R. So total number of trees which are possible by keeping this as a node will be obviously L star R. Okay, so here we will be just doing left star right. Okay, and this we have to obviously store or memoize somewhere, so we will be doing a dp of n equal to answer, but before that we have to initialize dp. So let us initialize it globally, and we have to dp dot resize n plus 1 solve n, and if the value is present in dp, if dp of I is not equal to minus 1, then return dp of I. Okay, not I, it will be n, otherwise dp of n equal to answer, and assign all the values for int I equal to 0, I less than equal to dp dot size I plus plus, and dp of I equal to minus 1. It less than dp of such size. And okay, so I think a code is done from our side. Let us run it and check whether there is any error or not. dp of n equal to, okay, we have to return as well, as it is an integer function. It is not answer, it is temp. Okay, all the cases are running successfully. Let us submit it. Okay, this was our bottom up, or it was our top down approach. Let us now understand bottom up approach. So in from bottom up, we have to start from 0. So we will initialize dp of 0 equal to dp of 1 equal to 1, because if we are encountering 0, or for example, let us consider this case 1, 2, 3, and for this node I am calling my function for this node. So on left hand side I minus 1 will be 0. So for 0 we are here, it is nothing, so we will be just returning 1. It is dp of 0 is equal to dp of 1 equal to 1, and here we are traversing for each and every node for number of nodes. Okay, so let us also traverse here for int I equal to 1, I less than equal to n, I plus plus. Here we will be just writing 2, because for 1 we have already taken care. Okay, dp of 0 equal to dp of 1 equal to 1. Okay, and now if I am giving you 3 nodes 1, 2 and 3, which is our loop of particularly I. So inside this I have to check for each and every node that what are the number of possible binary trees. If I keep this as a root node, then I will be keeping this as a root node, and at last I will be keeping this as a root node. So it will be basically we have to run another loop among these values, and let us name it j. So for int j equal to 1, j less than equal to I, and j plus plus, because these are basically traversing for each and every node that we have taken by I. So what will be our left total number of trees which are possible is equal to dp of j minus 1, 1, because if I am standing right here, then what is the total number of possible? It is j minus 1 obviously. And what are total number of right side possible? Because here we are taking total number of nodes as I. So total number of nodes on the right hand side, if I keep this as a root node, will be I minus j, and right side trees that are possible is equal to dp of I minus j, and I will be just temp equal to plus equal to right star left. Okay, int temp equal to 0, and for each and every node I will be just updating dp of I equal to temp, because I will be getting the value for n equal to 3. Oh, okay, let us dry run this particular case for n equal to 3. Let us erase these things. If I give n equal to 3 for these 3 nodes, so initially I is equal to 1, not equal to 1, because I will be starting from 2. Okay, so it is starting here. So initial loop will be having just 2 nodes, because j will be starting from 1 and j equal to 2. So for j equal to 1, what is my left? It will be j minus 1. So j minus 1 will be 1 minus 1 equal to 0, and I minus j, for j equal to 1, I minus j will be equal to 1. So for 1, dp of 0 equal to dp of 1, it is equal to 1. So for this particular node I can have just one binary tree. So n, not ns, but temp we have taken. Temp will be having initially 1 as answer. Now j will come to this node, so j equal to 2. So left hand side will call dp of j minus 1, so it is equal to 1 here, so it will return just equal to 1, and dp of I minus j, and as I is equal to 2, so j is also equal to 2, so 2 minus 2 equal to 0, so dp of 0 equal to 1, so it will be also returning 1, and 1 star 1 will be always equal to 1, so here temp will be updated by 2. Similarly, I will be coming for this value, I is equal to 3, and now j will be here, so it is having calling dp of 0 because j is here, and dp of 2, but dp of 2 is already equal to 2 because somewhat here we have updated it, because dp of I we updated equal to 2, so it will be returning 2, so 2 is equal to dp of 2 equal to 2, and it is equal to 1, so 2 star 1 equal to 2, so dp will be updated 2 plus 2. Okay, now j will be coming on this node, so on left hand side dp of 1, right hand side dp of 1, so 1 star 1 equal to 1, so again temp will be incremented by 1, and on right hand side, okay, no, all the cases are being taken care of, so for 3, 2 plus 2 plus 1 is equal to 5, which is answer for our case. So let us return dp of n and let us run it. I hope it should run pretty well. Temp, okay, it is working perfectly. Okay, accepted. Now let me tell you a secret. All these things that we are learning, those who have prepared for gate or those who are preparing for gate, they should be knowing this, because this particular series, for example, if I give you 3, then total number of structurally possible is 5. If I give you 4 nodes, then total 14 such trees are possible. It is particularly given by a series called Catalan number. Like Fibonacci series is there. Similarly, Catalan number series is also there, and its formula is 1 upon n plus 1 factorial into 2ncn. This is the formula of Catalan number. Let us check for n equal to 4. So for 4, 1 upon 5 factorial 2ncn, so it will be 8c4. 8c4 will be 8 into 7 into 6 into 5 upon 5 into 4 into 3 into 2. 5 5 will be get cancelled, 4 into 2 8 is cancelled, 3 3 is 2, it will be 7 into 2 equal to 14, and as we know answer is 14. So what will be the time complexity for unique binary search trees? It will be O of n square. It is because this loop we are running from n, and initial loop in worst case will be also running from n 0 to n, so it will be O of n cross n be O of n square. Okay, so this is it from my side. This problem was a good problem. It's a decent problem, we can say, of having dp tag and tree tag. So even though people are not able to solve problem of trees also, and if we combine dp on trees, it's a pretty good question, pretty good tough question we can say, but we understood it from complete scratch. You might find video to be considerable amount of time. It's quite long also, but I have tried to cover each and everything, and each and every concept which is required for this tree. We have covered it from scratch. We have also seen its code, bottom up approach, top down approach, everything, time complexity as well. So please give this question a try, and we will be meeting in the next video. Till then, keep working, keep hard working. Thank you very much to all.